No, I'm not like a space stress.
Hello, 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 everybody. Welcome to the 102nd, I think, the 102nd edition of Space Drafts. I'm Lily Whitler. I'm a PhD student at the University of Arizona. I'm joined here by many of my co-organizers, and we are very happy to have you here with us today. So Space Drafts is part of an international network of astronomy on tap, where we astronomers like to come together in bars and pubs across the world and share the joy of astronomy with you guys, the public. So here in Tucson, the show works. Can everyone hear me? Good? Yeah, cool. So here in Tucson, we'll have two speakers, approximately 20 minutes each, with a 20-minute intermission in between. As many of you who are regulars here know, there we go. Yep. As many of you who are regulars here know, we are right next to this. This is putting in and out. I swear, we tested all of this half an hour ago. Yeah. Many of you witnessed us testing it half an hour ago. Okay. Cool. I'll just keep talking and hope it doesn't disappear again. Anyways, train tracks. If a train comes and you cannot hear the speaker because it's blowing its horn too loud, we'll wait it out, and as we're waiting it out, just raise your glass, toast the train, and say choo-choo. It's our tradition here at Space Drafts. We have merch over here, stickers, some magnets. I think we have some pint glasses left. Yes, no, maybe so. So feel free to come and check that out at the intermission. I believe that is. Oh, do you have a trivia question? Okay, so at least Jeniveve will have a trivia question. If you would like to raise your hand and answer it during the talk, the first person to get it right is welcome to come to our merch table and get a free sticker or a free magnet. And I think without further ado, I will let Jeniveve take it away. So Jeniveve is a PhD student at Steward Observatory who is going to be telling us about the astronomical version of Pokemon.
Alrighty. Hello, everybody. My name is Jeniveve. I'm a PhD student. I'm a fifth-year PhD student at Steward Observatory. So I'm doing an astrophysics PhD. And I am excited today to stand before you and tell you that I am much nerdier today than I was yesterday on account of making this talk. So hopefully you will enjoy the fruits of that labor. So I want to start us. We're gonna.
Oh, sorry. That was my bad.
There we go. Okay. I want to start us with a reminisce. All right? Let's think back to the summer of 2016. The jeans were a little skinnier. There were less cameras on the back of our phones. It was election year, kind of similar to this year. 2016, the summer of 2016, was the year I graduated high school. So, aging myself a little bit here. What else was the summer of 2016? Does anyone want to yell out something? Pokemon Go! The summer of Pokemon Go. Now I, especially as a high schooler, but even still now, was a little bit of a contrarian. I read Harry Potter years and years after the rest of my classmates. I still haven't seen the Hunger Games, and I didn't play Pokemon Go. I didn't grow up with Pokemon. I didn't play a lot of games growing up. My mom was kind of like an anti-technology type of parent. So I didn't have really an emotional attachment to Pokemon. So I kind of sat this one out, but observed the chaos of everybody else being very excited about Pokemon. And then we fast forward to spring of 2021, a year into the pandemic. It was my first year of grad school, second semester. We're still remote, right? All of my classes are on Zoom. Learning is definitely happening right now. And in the spring of 2021, a game came out called Pokemon Snap on the Switch. Now, the gameplay of Pokemon Snap is literally just that you take pictures of Pokemon. That's the entire gameplay. You try to make better and better pictures of Pokemon. I love this game. Okay, this is what I want out of every gaming experience. So I count this as the birth of an extremely casual Pokemon fan, that being myself. So I say extremely casual because I did have to do a significant amount of research to make this presentation. So, I am a transient astronomer. I focus on looking at transient phenomenon in my own research. And we kind of think of transient as the Pokemon of the astronomy world. So what are transients? That word is like kind of difficult to parse. A transient is an astrophysical phenomenon that changes brightness on shorter timescales. So short timescales can mean seconds, minutes, hours, days, years, or even decades. But we're talking like human timescales here. So you can see here, there's a little GIF of a supernova in a nearby galaxy and how its brightness changes over time. So think explosive phenomenon. And the study of these things is called time domain astronomy or transient astronomy. We use both interchangeably because time domain just means varying with time. All right, so when we talk about transients, we're talking about two different types of things. The transient phase space, as you will, has brightness. So how bright is this transient? How bright does it possibly get? How energetic is it? And time scale. So how long does it last? Is this a second type of thing, or is it like a year that it's lasting? And how long can we observe it for? So if we take this phase space, the one that maybe is the most common are variable stars. So if we take variable stars here, what are variable stars? Most common transient event. Variable stars are any stars whose light varies. So, pretty obvious there. This is an extremely common phenomenon. There are two main classes of variable stars, intrinsic and extrinsic. Intrinsic variable stars are stars whose internal physics is causing them to vary on timescales we can observe, either eruptively or pulsationally. So literally the temperature or pressure inside the star is changing over time, and we can see that in the light curve of that star. An extrinsic variable star is something that is changing not due to its own physics in the internal star, but something exterior to that. So you can have an eclipsing variable star. That just means that it has a friend that covers it half the time, so you don't see as much light sometimes. So it's an eclipsing variable star. Or you can have a rotational variable star. And that just means probably there's like a dark spot on one side of the star, so when it rotates, it looks dimmer when the dark spot is in front. So famous variable stars, intrinsic variable star is Betelgeuse. I won't ask you what type of intrinsic variable star Betelgeuse is, because that's a trick question. It's both. It is both an eruptive and a pulsating intrinsic variable star. You might have seen the news coverage about its great dimming. That was an eruptive event, but it continuously pulsates as well. And then an extrinsic variable star is Algol, also known as the demon star. It's Medusa's eye in the constellation Perseus. Does anyone want to take a guess at what kind of extrinsic variable star Algol is? Just yell it out. Eclipsing, that's correct. It is an eclipsing variable star. And it's observable enough that we think it's called a demon star because astronomers were able to actually see it varying, astronomers in early Arabic empires. So let's say, okay, we're going back to Pokemon. What kind of Pokemon is a variable star? Well, a variable star is a normal type Pokemon. This is a very common object. There's many different kinds. It can be all sorts of things. So we can call it a normal type. So, okay, we've assigned variable stars their Pokemon class. And now we're going to go through all the different types of variable objects and transients and give them all Pokemon classes, because I think it's a good way to think about different types of objects, because like Pokemon, we as astronomers like to classify things into types. And when we give them types, there's obviously some diversity within that type. Different types of Pokemon are in like the big class of normal type. Okay, so let's talk about this bottom corner here. We want really short time scales and not very bright. These are M-dwarf flares. They exist down here. So M-dwarf flares are flares in the most common stars in the sky. So the most common stars are stars between 0.08 and 0.6 times the mass of the sun. So we're talking tiny, tiny stars. And while they're extremely common, they're difficult to see. But they're exciting because they might host planets around them, and so and because they're long-lived, you might have longer-lived life in those planets. But when we've been observing M dwarfs, we can see that they have these magnetic flares, these huge bursts of UV light, and that is basically flooding the planets around them with UV radiation, and that could be causing mass, like maybe would life even exist through these things. So that's a field of study that's very exciting for exoplanet astronomers, in addition to stellar astronomers. And the most famous of these M-dwarf stars which has flares is Proxima Centauri, which is the nearest star to Earth. It's only 40 light years away. So, very nearby. These are my bug-type Pokemon. They're very small, kind of insignificant, but they're exciting in their own way. Lots of people like bug-type Pokemon. All right. So now we have our bug types. What's right in the middle here? We have novae. So novae, or classical novae, are the result of interaction between two different types of stars, a white dwarf and a donor star of some kind. So a white dwarf is a really compact object that is held up by electron degeneracy. So basically, the electrons don't like to be on top of each other, so that's keeping the star afloat. It's a very compact, small object. The sun will eventually become a white dwarf. Now, the donor star around the white dwarf, if it's close enough, can dump mass on top of the white dwarf. And because the white dwarf is an extremely hot, dense object, the material, when it falls onto the white dwarf, will ignite and create these little eruptions known as novae. And these are non-terminal explosions. The white dwarf still exists after the eruption on the surface of the star. And they can reoccur, because if you have a big accretion disk that has mass falling into the white dwarf, maybe you only blow up a little bit when you have your eruption. So a famous example of a classical novae is T Corona Borealis, which is that novae that everybody has been telling you is supposed to happen just as soon as you look up in the sky. Surely it will happen this year, but this year is almost over and it hasn't happened yet. So, but keep a lookout for that. It might happen. Who knows? These are our grass types. I'm calling them grass types because they steal mass from their donor star. We got a little grass type over there. All right, so now let's talk about supernovae, now that we've talked about novae. Supernovae is what I do in particular. I'm most excited by core collapse supernovae. Core collapse supernovae are the explosive deaths of stars greater than 8 times the mass of the sun. At their end of their lives, they fluff up, they throw off mass, you have these extreme mass loss events, and the amount of mass that they lose determines ultimately what type of core collapse supernova they are. You can think about this as like what Pokemon they end up being. But ultimately, all of them will run out of fuel in the center of their cores and will try to start burning iron, and iron doesn't create any more energy, so they will collapse in on themselves under their own gravity and ultimately explode outward because particles don't like to be on top of each other. So have these huge explosions that cause all kinds of explosive chemistry that's responsible for you and I being here today. All the organic molecules in the universe are made by core collapse supernovae. And they also affect star formation around them. So they can blow holes in glass clouds and compress glass clouds so that you can have new star formation as well. So famous core collapse supernovae include supernova 1987A. Some of you in the crowd might remember 87A. I don't. I was not alive. But it was the closest supernova to us in recent history, and it was naked eye visible. So fingers crossed for those of us who are too young to have seen that there will be one in our lifetimes that we'll be able to see. And then also, famously, Cassiopeia A, which is this beautiful image down here at the bottom, which is maybe one of those supernova remnants that you've gotten to see, is a famous supernova, core collapse supernova in our own galaxy. So these ones are going to be fire types. I think this is self-explanatory. There are these huge bursts of fiery balls of fire. Okay, so we have our core collapse supernovae. Now there's other types of supernovae. The main one is type 1a supernovae. Type 1a supernovae, similar to novae, require two stars, one of which needs to be a white dwarf. So we think that there are multiple ways you can come up with type 1a supernovae. One, you need a white dwarf and a donor star, similar to a novae situation, but you dump enough mass onto the white dwarf that it doesn't, instead of just having a surface explosion, the whole thing explodes. Or you can take a white dwarf and another white dwarf, spiral them in together, slam them into each other, you have a merger, boom, now you have something that's too big to hold itself up, and you have an explosion. So the explosion is caused by the fact that electrons don't want to be on top of each other, and if it's too heavy, it literally explodes outwards to avoid that property. So these are extremely luminous because they do not have a remnant at the end. They literally destroy themselves completely. And a notable one of these is Kepler's supernova. That was the most recent supernova observed in the Milky Way galaxy. So these are rock-type supernova. We've got an extremely dense object that is blowing up. Sounds like a rock-type to me. So now we have our LBVs off here in the corner. I'm going to go off in kind of a random order here, but I promise it makes sense. So luminous blue variables, or LBVs, are massive evolved stars that are famous for being supernova imposters. They can be bright enough that everybody thinks they're a supernova, but then turns out they didn't disappear at the end of their lives. They're still there, and they might have another LBV eruption in the future. So luminous blue variables are just big stars that are variable, and they're pulsating and also eruptive, and we think that they exist, these eruptions, either as a result of binary interactions with another big star, or huge, massive winds around these huge stars. So these stars are like extremely large, greater than 40 times the mass of the sun. So they're doing all kinds of weird stuff that we don't really understand because they're rare. They have extremely short lifetimes, and we don't understand their explosions that well, although there is some evidence that they have kind of periodic eruptions in some cases. The most famous of these is Eta Car, or Eta Carinae. This is an artist representation of Eta Carinae here. There's actually historical records of Eta Carinae like exploding in the sky and people seeing it. Of course, it's not terminal, it still exists today. These are going to be our poison types. I can't explain to you why I decided these were poison types, but it just felt right. Okay, so now we're going to go more luminous than a supernova. We'll call these very aptly a superluminous supernovae. This just means it's a supernova that's really bright. 10 times as bright as a normal supernova. It can be any type of supernova. Usually we think these are probably supermassive stars that are exploding, that are just super, super energetic, and that's what's causing that explosion to be extremely bright. This is a really, really diverse class of things that's poorly understood and extremely rare. Most of the superluminous supernova we're observing are millions of light years away, and because they're so luminous, we're able to see them here on Earth still. So these are going to be our flying type. They're flying type because they could be anything, and famously flying type are never just flying type. So we got our little Charizard on there. And here, nestled in amongst all of the supernova, are tidal disruption events. These are not supernova. These are not even stellar objects. This is a black hole that's shredding apart a star. So a star passes close enough to a black hole that it can be tidally disrupted by the black hole's gravity and pulled apart and shredded. And then that black hole accretes that material that it shred off the star. So ultimately, there's all kinds of weird stuff that's happening with this star. You've got streams of star material that are intersecting with each other and causing all these kinds of like jets and interactions. And it's a really cool type of object, but you probably maybe have never heard of them because there hasn't been one that's like close enough that everyone has like seen press releases about them. The most famous one is Assassin 14Li, which just me saying that should tell you that it's not very famous at all, if its name is Assassin 14Li. So these will be our fighting types though, because they're literally tearing apart stars. That's the process that's happening here. So it makes sense that it's a fighting type Pokemon. We've got Killinove. These are probably one of the most famous types of transients, even if you haven't heard of them called Killinove before. Killinove are the interaction of a neutron star and likely another neutron star. I say likely because there's a slight possibility it could be another black hole, like a neutron star and a black hole. But for the most part, we think it's probably a neutron star and a neutron star. So similar to the scenario where you have a type 1a supernova with 2 white dwarfs spiraling in, here you have 2 neutron stars, which is the end result of massive stars exploding. They're slamming into each other, creating this huge burst of energy, and that has gravitational waves as well. So we can actually detect those gravitational wave signatures in addition to seeing the light from these objects. We've seen that in one case, even though we have been looking for a very long time, in the case of AT 2017 GFO. You might know this one better by its gravitational wave name, but this was the first ever observed gravitational wave signature that had an optical transient with it. So we keep looking for these because these are really exciting transients. It's multi-messenger astronomy, so that means we can find both optical, like both light and gravitational wave signatures from these things, but we keep looking and keep coming up empty, and that's partly because gravitational wave detectors have poor localization, so it's hard to like look at the sky and be like, for sure it's coming from this point, even if we find transients in that patch of sky. So our Killinova, because they're exciting and everybody wants to give us lots of money to look for them, are our electric types. These are our Pikachus of the transient world. And we go a little bit more energetic here. We have gamma ray bursts. Gamma ray bursts are literally what they sound like. It's a burst of gamma rays that is caused by one of 2 processes. If it's a short gamma ray burst, literally it lasts a few seconds. A short gamma ray burst is, a few milliseconds is a short gamma ray burst. And a short gamma ray burst is the result of a neutron star merger. So you could possibly get a Killinova as well as a short gamma ray burst. And then you can have a long gamma ray burst, so this is of the order of seconds. And a long gamma ray burst is a result of a core collapse supernova that has no extra layers. So if you have like think of it as like a bald massive star, so that the jet can completely destroy the star, and that's how you get a jet beamed at you and you get a gamma ray burst. So these are incredibly energetic because there's a jet pointed at you that you're seeing of like very highly excited particles. And so these are really energetic, and we generally can see them quite far away because you have material that's pointed directly at you. The most famous of these that you might have heard in the news recently is GRB 221009A, more well known as the boat, or the brightest of all time. So there's lots of work here at Steward and at Tucson in general on GRB objects. And because they have a nice little jet, this is obviously a water type Pokemon. All right, so we're getting to the end here. We have 2 more different types of Pokemon to talk about. Number 1, we have fallback transients. Now, these are near and dear to my heart. Fallback transients are basically when you create a black hole, so stars greater than about 20 solar masses, you create a black hole, but instead of having a visible explosion, the majority of the mass of the star falls back into the black hole. So you could think about it as kind of like a star imploding rather than exploding. And this causes the star to appear to disappear in the sky. So the issue here is that because it's easy to find something that gets bright,
Choo choo.
Yeah. All right. So it's easy to find something that gets bright. All the things I've showed you so far are things that brighten in the night sky. But it's hard to find something that disappears. You have to be looking at stars and checking whether or not they're still there in every single frame, rather than just saying, oh my god, there's something new here. So it's a little bit harder to find these. And because of that, most of our understanding of these objects is like completely gone. We don't understand what these things are. We don't understand if they even have an explosion. Is it like a small, tiny little explosion that might look more like a nova? Or would it just be like a lower luminosity type supernova? Or does it just completely poof out of existence and you don't see it at all? We don't understand if it has a jet, what kind of energy these objects might have. We have no idea what's going on with these. The most famous of these is down here in the bottom. This is NGC 6946 BH1. It's in the Firework Galaxy. You can see there's no star there. Turns out when you look with JWST, there is something there. So either it's a black hole that's somehow still bright, maybe the accretion disk is causing it to be bright, or it's not a black hole at all, and we've just been hoping that it's a black hole. So these are going to be our ghost types because they're literally not there. We're hoping that they exist. They should exist. We know black holes are made by stars, so we should have these. But we're still vainly looking for them. And we'll put Gengar down there. And finally, up in the top corner, we have active galactic nuclei. So you might have heard about AGN. AGN are the results of a supermassive black hole in the center of a galaxy that is interacting with the stuff around it. So you have lots of accretion onto this supermassive black hole, and this causes, you have like lots of variability. I don't study AGN. AGN you start to get into the galaxy realm once you talk about AGN. These are incredibly energetic, so you can see them much further away than you can a typical like stellar type transient. And if they're extremely powerful, it's called a quasar. But these are exciting because they emit in the full spectral range. You can literally look at any type of light and see and study an AGN. Most famous AGN are M87, which is that like donut picture from EHT you might have seen, and Sen-A. So these are like nearby galaxies. These are going to be our dark types because it's a massive black hole. So, all right. We have a bunch of Pokemon. I've probably bored you talking about all these different types of transient objects. Now what? Well, we have to catch them. The reason we say transients are the Pokemon of astronomy is because we care about catching transients a lot. So we have to catch all of these transients and observe them. So let's talk about what the best Pokeballs are for catching transients. So, tip number one when trying to catch a transient is you need to look all the time. Emphasis on all, okay? So you want to be looking at the entire sky every single night. Bonus points if you have multiple different telescopes looking at the entire sky every single night. So here we're going to go through a couple of Pokeballs here. We got a regular Pokeball. This is Pan-STARRS. It's it's a transient survey in Hawaii that looks at the night sky every single night and reports what they see. We have our heavy ball. This is Assassin. Assassin is basically a bunch of, you can think of it as like Canon cameras that are pointed up at the night sky at a bunch of different places around the world. And so they can only find the really super bright things, but they're really good at finding the super bright things because they're looking at the entire sky at any given moment. Because at least some of the Earth is dark at any given time. We have our Great Ball. This is Atlas. Atlas is most famous for finding near-Earth asteroids, but because they're looking up at the night sky all the time anyways, they also find a lot of transient events. And then we have our Ultra Ball, which is ZTF. Now ZTF is like the workhorse of transient astronomy currently. It's a very exciting survey that finds the vast majority of transients that we study. However, there's a couple other ways you can find transients. You can, tip number 2, look where you know transients will be. So targeted surveys are surveys that focus on galaxies or specific parts of the sky in order to, like, because those galaxies or specific parts of the sky have higher rates of transients. So these surveys are better at catching transients quickly. So this is going to be our quick ball. This is DLT-40, the distance less than 40 megaparsecs supernova survey. 40 megaparsecs just means it's a nearby galaxy. If it looks pretty, it's probably within 40 megaparsecs. That's the way I explain this to people. I'm part of DLT-40, so we look for nearby supernova, and by looking at these same galaxies and imaging them for like every single night, 3 or 4 times if we can. So we can really find a supernova or another transient within 24 hours of it exploding and get right on sky and catch that really quickly. The other thing you can do is just stare at any patch of sky, anywhere, because transients happen everywhere. They're happening out right now across the entire night sky. There's a bunch of different types, and so they're everywhere. And so you can think about these as our like more region-specific Pokeballs. This is a safari ball. We can think about TESS as this. So TESS is the Transiting Exoplanet Survey. So they literally look for exoplanets in the night sky and see if stars are dimming and look for exoplanets in that way. But because they're imaging an entire patch of the night sky at all times at like 30-minute cadences, we get really, really good dense light curves of these transient events that are also happening in that patch of sky. All right, so there's the 2 tips of how we find them today. And this is what the Pokédex looks like so far. So every year we find about 20,000 transients or transient-like events. And they span the entire range of Pokemon types that we've talked about today, plus a few extras that I didn't touch on. And that's very exciting. We do a lot of great science with these things. But in the future, we're going to be wanting extra things and wanting to learn more about transients. And to do that, we need to look further. So a few things we want from our future transient surveys. One, we want it to be all sky. Looking at the entire night sky is incredibly valuable. It helps us find all kinds of transients and things. And that way we catch anything that happens in the night sky. Number 2, we want it to be high cadence. So that means we just want to image that sky fairly regularly so we can see how that light curve, how that brightness of that object evolves over time. We also want deeper images. So deeper images means we want to be able to see further into the night sky. We want to see things that are millions of light years away instead of just tens of thousands of light years away. And then we also, because we have a larger area of search, if we're looking deeper, we'll also be able to see thousands of more things as well, which means more rare stuff, which would be very exciting. And then also we want color. Color is very important because when we see color for the different evolution of these transients, they can tell us something about its temperature and its energy, and then also what the progenitor of that transient might have been. So you want to know what kind of object it came from to begin with. So this is our master ball. This is the ideal situation, and our master ball is already built. The Rubin Observatory is down in Chile. And its transient survey is called the Large Survey of Space and Time, or LSST. We're very, very, very excited for LSST, and the Rubin Observatory, as we're speaking right now, they're changing out their commissioning camera for the actual science camera. They will be on sky in the spring. So that's really exciting. We're going to have lots and lots of new transients to look at, and this is the master ball of transient astronomy. So now let's talk completing the Pokédex of transients. Here's your trivia question. How many transients do you think we will find with LSST? Is it 1,000 a day, 10,000 a day, 1 million a day, or 10 million a day?
1,000.
1,000? It's not 1,000. What? Yeah. 10,000? It's not 10,000. Do you wanna? Yeah? A billion?
No, a million.
A million? It's not a million.
Let's go 10 million.
All right.
Is it 10 million?
It is 10 million. So, okay, we're gonna take our Pokemon. We're gonna make them real small. That's how many transients we'll find a day with LSST. That's how crazy this master ball is. So we're literally supersizing our ability to look for transients, and in that, not only will we find hundreds and hundreds of millions of all of these types of transients, all of these Pokemon, but we'll also probe everything else. And all that stuff is stuff we don't even know to look for yet. You know, I told you about fallback transients and how we've never found one, but we're pretty sure they exist. There's stuff out there we don't know exists yet because we haven't ever seen it. And now with LSST, this is going to be our chance to look for these things, to look for the unknown. So, this little guy right here is an unknown, just in case you guys were curious. With that, I'll leave you guys for questions. And thank you.
So I'm just kind of curious. You touched on this, but what kind of like spectral bands are you observing in the LSST?
Okay, so your question is, what kind of spectral bands do we observe in? Yeah, so I'm an optical and near-infrared astronomer. So I use the ground-based telescopes here in Arizona, but we can observe these in any band. So these gamma ray bursts are observed by space-based telescopes in the gamma rays, and also in X-ray. Active galactic nuclei can be observed across any wavelength, and you know, there's all these different things. We want to get as much color information as possible. And when I say color, I don't mean just like the color your eyes see, but also the multi-wavelength information, like UV and IR, X-ray, all that stuff. Yeah.
So, if we can see 10 million a day, how far away are they?
Yeah, that's a great question. Yeah, the question is, if there's 10 million a day, how far away are these things? So it depends on the type of transient. So the further up you go in this brightness scale, the further away you can see it. So right now we're currently observing GRBs that are like millions of light years away. But with something like LSST, we might be looking at tens of millions, maybe even billions of light years if we're lucky. But like something fainter, we're not going to be able to see that quite as far. But we're going to be probing deeper than ever before, and I've seen like estimates that like are like insane. But even then, like the 20,000 that we're observing today are all like within hundreds of thousands of light years away for the most part when you're talking about supernova at least. So just think about how far, and it's like a volumetric. So you go further out, you x, you double and double and double. Yeah.
If you're observing 10 million of these a day, how are you keeping track of that? Like, is it automated, or is there a human looking at everyone being like, this is one, this is one?
Yeah, so that's a great question. The question is, if we're observing 10 million a day, how on earth are we keeping track of all of them? So that is a huge part of the budget for LSST. There's a whole bunch of machine learning and classification stuff that's going into this stuff. And there's also a lot of work that's being done on the infrastructure necessary to make pipelines and data production work. Sorry, I'm trying to get louder, but I don't know if it's working. And so basically, this is a question astronomers have. We have for the people who are working on LSST and on Rubin. I asked one of the leads of LSST this actually last week. Like, okay, how is my interaction with this data going to be? The short answer is there's all different kinds of groups that are building tiny brokers to help us filter out the things we care about. And then in addition to that, there's the huge data load that all of this 10 million alerts and objects, and that will be publicly available for us to grab when we want. Of course, it's going to be, we're not being super environmentally friendly by storing all this stuff, but that's the price we pay for 10 million a day. So there's that. All right, thank you guys. I have to go, but please find me afterwards if you have questions.
Thank you so much. I did not realize some of those were transients, and I probably should have, actually. So it is now 8:17. Let's say be back here by 8:35 after intermission for our next speaker. If you're going to go get a drink, please remember to tip your bartender. Borderlands has been very kind to let us run shows here for 10 years. And feel free to also come talk to us at the merch table. Feel free to talk to Jeniveve and ask her more questions. And I'm going to shut up now before this train interrupts me.
That's good.
You freaked out me behind you. I wanted to hit your head. That's why I'm
Just get the paper signs.
Nope. Let's see. And
intermission. We will get started with our second talk now, which is by Josh Liberman, who, title slide has vanished.
Sorry.
Is an optical sciences graduate student who is working with the MegaUX team.
Hi, I hope everyone is staying warm on this chilly Tucson evening. I'm Joshua Liberman. I'm a graduate student at the University of Arizona. And today I will be telling you about the search for alien worlds from Earth's largest telescopes. So I wanted to start with a bit of background and just how I got to where I am today. So I was born in Massachusetts, and my town is most famous for its furniture store. And yes, this is a furniture store, even if it does not look like it. I got into science from a young age, so here I am at a mad scientist birthday party, and I was making potions, I believe, and the patch of grass underneath this table never grew back, so that's kind of a fun fact. And following graduation from high school, I attended Colgate University, affectionately known as the Toothpaste School. It's a small college in the middle of New York State. And it was here where I really got into citizen science for astronomy, but particularly using household cameras like this Canon you see here to try and look for planets. And that brought me to a much larger citizen science project called Project Panoptes. And I kind of fell in love with it because how could you not like this little cute robot, which is it's made up of 2 of these Canon cameras, which you can buy commercially. But I really wanted to, after this, start working with astronomy devices that were a little bit bigger. So the summer after my junior year of college, I used a grant from my university to intern at the Keck Observatory in Hawaii. So Keck, fun fact, is actually made up of 2 twin 10-meter telescopes, and I'm a big fan of twin telescopes because 2 telescopes is always better than 1, in my opinion. And so here's me standing in front of the dome of just one of these 10-meter telescopes. And I also had the opportunity to get my first professional observing experience on a telescope. So in the foreground here is my Corgi Squishmallow, but then in the background is a photo of the center of our galaxy. So following graduation from Colgate, I took a position as a researcher at Caltech to gain more experience developing instruments for telescopes. And it was here where I got my first hands-on experience with optics. So I can be seen in this image giving a thumbs up after helping to align some sort of optical system. I can't actually remember which one. And then again, the Corgi Squishmallow, which means that this involved more observing with the Keck telescope. But this time, we tried out an instrument that our group had built. So this was pretty exciting. And after a year of doing this research position, I began graduate studies at the University of Arizona in the College of Optical Sciences. And within my research group, this involved even more travel, where we go from Arizona to our observing site in Chile at Las Campanas and back again. So why do all this travel as an astronomer? Well, it's not a coincidence, but we build telescopes in remote locations, and as opposed to, say, my home state of Massachusetts. Why not build a telescope outside my furniture store, for example? Well, aside from the practicalities, there are a few reasons that make some of these remote observing sites the best sites in the world for astronomy. So in Chile, for example, in the Atacama Desert, one reason, which may be obvious, is we get very clear skies. So you can see that here. We also get a lot of darkness, a lot of dark skies. And so you may have noticed in Tucson that a lot of the street lights look a little funny, like they're different colors. And that's actually not a coincidence, but it's because Tucson is trying to keep the sky darker for astronomers in other parts of the state who want to use their telescopes. So dark skies are very important. But also, we want to be above the clouds, ideally. And this is kind of foreshadowing for something I'll be talking about later in this talk. But the higher up you can be and the more clouds that are beneath you, the better for your observing. So now, what do these professional telescopes look like? Well, to answer this question, we're going to go inside the Keck telescope. So here in this video, you can see the Keck's 10-meter primary mirror slewing into home position. And so I'm going to break down just a few things in this image. We can see in the back here, is what we call the primary mirror, the segmented mirror. And then the light is going to bounce off this primary and hit the secondary mirror shown in the foreground here. And then from there, it's going to go into this central hole and it'll hit a tertiary mirror. And this third mirror will direct the light to different instruments within the telescope. But let's talk a bit more about this segmented mirror that Keck has, because I personally find it really cool. So a segmented mirror design is actually a combination of smaller mirrors, like this one here. And each mirror forms one little piece of this larger hexagonal sort of honeycomb structure. And on the back of each of these mirror segments are actually this whole web of electronics. And that's because as the temperature changes for your mirror segment, it's going to bend and flex. And so what these electronics will do is if one of the individual mirrors bends, then these electronics will tell all of the little segments to also move in unison. And in this way, we have a segmented mirror which functions like a continuous unit, so to speak. And so here I just want to introduce the trivia question, which you can think about. The answer will be at the end of this talk. But the question is, what is the world's largest optical telescope? And if you're looking at the options and you're a bit surprised, there is indeed a telescope which is just called the Very Large Telescope. And I didn't name it, so don't blame me. So just keep this question in your head for the end, and I will be telling you the answer at the end of this talk. But now, we're going to look for some worlds. We're going to try and find some planets. So how do astronomers find exoplanets with large telescopes? Well, there are a few different methods we can use. But first, I want to introduce, well, what is an exoplanet to begin with? So that's just any planet that's outside of our solar system. And here, I included a few of my favorite artistic renderings of what planets, alien planets, might look like. So one very popular method for finding these planets is what we call the transit method, where you're going to measure the brightness of a star. And as your planet passes in front of the star, you'll observe a dip. And so in this way, you can indirectly observe the presence of a planet. In this next popular method, we have a sort of tug of war between a planet and the star, and this is called the radial velocity method. And again, this is an indirect way of finding these planets, where as you measure the star's color over time, what you're going to see is that as the planet tugs the star towards us, the star color is going to look more blue. As the planet tugs the star away from us, you're going to see the star's color appear more red. And finally, we get to my favorite method, direct imaging. And with this method, you can actually observe light from the planets themselves. So you're probably wondering here why I'm showing just this time lapse with little blobs moving around. And you've probably seen in various articles about alien planets various artistic renderings of what that might look like. But in this time lapse, what I'm showing you is the real deal, because these are actually like directly imaged planets and not artistic renderings. And what's also really exciting, if you're a physics nerd, is this is also a really good demonstration of a fundamental property of physics. So first, here at the center of our time lapse, we have what we call a coronagraph, or a starlight blocker. And then next to it, these are all the planets that are moving around the star. And you can observe from this fundamental law of physics that the planets closer to the star are moving more quickly, whereas the planets further away are orbiting more slowly. So again, with this direct imaging method, when we get light from the planet itself, we can begin to understand what the planet's atmosphere contains. So here, when we get light from the planet, we can then get the planet's spectra, or essentially break down what sort of molecules exist in the planet's atmosphere, like water perhaps. And that's what makes this technique very powerful and the key to finding alien life. So we typically use a metric known as the Goldilocks zone for finding these habitable planets. And that's just based off of what we know from living on Earth, what makes for life. And so that means the planet has to be located in a region that isn't too hot or too cold, but rather is just right for liquid water. And also, we expect that an Earth-like planet, or a planet that contains life, should be roughly Earth-sized. So why haven't we found any of these Earths just yet? Well, the short answer is that it's really difficult. And so one of the main reasons is this atmosphere that we have above us. And it's really bad for astronomy because it's going to cause our stars to do a little dancey dance. And if you watch any dance competition shows, then you might be a bit familiar with this dancing of the stars in our case. And this is caused by these moving pockets of air within our atmosphere. So what this means is that instead of having this cool image that I just talked about of this time lapse, you instead get something that looks more like this. So when we take a video of a star from our Magellan telescope, we get this blob which is just moving around on our screen, and we really can't do much with that. So as you can see here, the atmosphere has effectively ruined our image. However, with this fancy technology called adaptive optics, we can remove these atmospheric distortions and get clearer images, almost like putting glasses on a telescope. So here you can see without AO, we have this sort of blurry, smeared image, but then with AO, you can suddenly see these two sources. So is this technology, this adaptive optics that I just introduced, good enough to detect Earth-like planets? Well, the answer is still no, but we're getting closer. The other problem that we have to face is that stars are really, really bright. So here's a star, and there are planets orbiting this star in theory. This is a simulated image. But the star is so bright, you can't see any of them. However, if we insert an optical device, our coronagraph, to remove the starlight, then all of a sudden, we can observe our planets. And again, this is a simulated image because we haven't actually taken direct images of Jupiter and Saturn in this way. But theoretically, this is what you can achieve with a coronagraph. So what are these coronagraphs? Well, it turns out that all of you in the audience actually possess a coronagraph right now, and you have it with you, and it's your thumb. So just by putting your thumb in front of the sun, you can block out the starlight, and this is probably the world's simplest coronagraph. So what we've covered so far is that if we want a device or an instrument to image Earth-like planets, we're going to have to go to our Build a Planet Imager store, and we want, of course, a heart, because every good Build a Planet needs a heart inside the instrument. And we're also, of course, we want a good telescope location. We want a system to de-smear our images or remove all of these effects from the atmosphere. And then we want our coronagraph or starlight blocker. And this way, we will hopefully be able to image Earth-like planets. So if only we had an instrument to do all this, well, it turns out we do, which is MagAOX. And this is an instrument that we have developed at the University of Arizona, and it's a system designed to image exoplanets. And just for the acronym, it stands for the Magellan Extreme Adaptive Optics System, but just don't think about that acronym too hard. It works for our purposes. So what is extreme adaptive optics? Well, I like to give people the very unhelpful answer that it's like regular adaptive optics, but more extreme. And I feel that's somewhat true. So what you can see in this comparison is we have, without AO, we have a blob. With AO, we can now resolve our source, and then by turning on extreme AO, the difference is kind of subtle, but you see that instead of having this sort of purple halo around our star, a lot of that has been removed. And so all of that area that's been removed, those were all effects from our atmosphere. So extreme AO is just like regular adaptive optics, but we're correcting for even more of our atmosphere. So our MagAOX instrument is pretty complicated. It's a two-stage optical system, and we have a whole series of cameras and sensors and mirrors that move. And so how do we use this instrument in Chile and also upgrade it? Well, we want to move it back and forth between our lab in Arizona and the telescope in Chile. So unfortunately, we haven't yet found a way to get our instrument to walk on its own, but that would be very convenient. So instead, what we do to transport our instrument is we use a bunch of graduate students and then also some shrink wrap. So here in this brief clip, this is us taking apart our instrument and probably annoying some of the neighbors in the nearby labs. We do tend to make a lot of noise in this process. And here, we're wrapping our instrument like a very expensive holiday gift. So after we wrapped our instrument and shipped it off to Chile, it's finally arrived at the observatory. And we're almost there. We're almost ready to take pictures of our planets. So here you can see the instrument on its flatbed truck, and we have followed it to Chile. And then here in this little corner, it's hard to see, kind of tucked away on a platform of the telescope, is our instrument, all ready for observing. So finally, we've covered everything we need to image our Earth-like planets, and we're ready to go up and open, but unfortunately, we have to wait behind wild horses because they also enjoy astronomy, and they tend to get a bit in the way. But there are quite a few animals at Las Campanas Observatory, and we love them dearly. So finally, we reach the telescopes, and it's finally time to open. So I thought I would show this time lapse where a horse just got in the way, but you can see here the dome opening and rotating from both the inside, and here you're going to see briefly after we take our photo op for the sunset. You're going to see here the vents open, and then here the dome is rotating, and we're ready. We're pointing to our first target. So finally, we've done everything we need to use our system, and I will just let the results speak for themselves. So here, what you've just seen is we've turned our blob into a completely stable source on the sky. And this is actually one of the highest quality images that you will see from a ground-based telescope. And if you look very closely, although it might be hard to see on this detector, you can see little X's moving across, like sort of in our image, and then also these circles moving away from our source. And this means that we've reached a physical limit in optics that we like to consider optical perfection. But additionally, there's even more interesting stuff going on in this object, because here you can see a symmetric pattern of these 3 dots. These 3 dots, but you also have an extra little dot here. And this turns out to be a companion to the star that we observed. So we looked at PiPup A, and then we turned on our system, and all of a sudden, we're able to see another star orbiting this first one that we couldn't see before. But we can do even better with our correction. So in this video, what we're doing is we're gradually increasing the ability to correct for the atmosphere. We're increasing the amplitude, so to speak. And so what you're seeing here, and I'll play this video again, is you see this sort of, these pink blobs, and you're seeing this dark ring kind of push the blobs out there, or out of the way, and make them go away. And that's our instrument correcting for atmospheric effects. And when we do this, we can see objects even closer to our star than previously. And so some of the results from our instrument are pretty promising. We've directly imaged a gas giant, shown here, that's roughly 10,000 times fainter than its host star. But additionally, we can observe disks, or nurseries for young planets, because in these disks, this is where young planets are potentially forming. And gaps in a star's debris disk can indicate the presence of planets. And so this, of course, was another image taken with our instrument. So, unfortunately, you might be a bit disappointed that I didn't show any Earths. Well, we're still not quite there yet. We're still searching for alien life. And so one of the options in the future is we want an even bigger telescope. So Arizona is building the Giant Magellan Telescope, and this will also have an adaptive optics system like the one that you saw previously. But we can also image without the atmosphere entirely by imaging from space. And this is the avenue which is considered to be most promising, actually, for finding the next Earth in particular. So this direct image was taken of a planet by the James Webb Space Telescope. And this is interesting because this is actually the coldest and the oldest planet that we've ever observed. But in order to image an Earth-like planet, we actually need to go even fainter, because Earth-like planets are about 10 billion times fainter than Sun-like stars. So for that, we're going to need a future telescope called the Habitable Worlds Observatory. I see we have some HWO fans in the audience. And it's designed to image Earth-like planets, and we're expecting it to launch in the 2040s. So that's by the way, that's an optimistic prediction given NASA. So as concluding remarks, we've seen that direct imaging is the key to finding alien planets, and astronomers can take pictures of these planets by correcting for the atmosphere and blocking out starlight. And we expect to find Earth-like planets within the next few decades, assuming that Habitable Worlds Observatory gets launched. So this is just a brief clip of the slide of the MagAOX team, and I was hoping to include a slide of all the animals as well. but I did not have time. But as an answer to the world's largest optical telescope question, well, let's first survey the audience. Which option do you think it is?
Question. Does A include both texts?
B.
It would be just one of the mirrors for Keck. So not both Keck telescopes.
Oh.
Yeah, I heard some disappointing. So if you said D, that answer is correct, but it's also a bit of a trick question because technically if you combine the large binocular telescope's two mirrors, you could get a mirror which in theory is larger than that of the Grand Telescope Canarias. But this is the largest single mount primary mirror on a ground-based telescope at, I think, 10.4 meters. However,
No. Salt's bigger.
Salt.
Salt's
Wait, it
11
is?
point. The primary mirror is 11.4 meters.
Never mind.
Well, it's tricky because the mirror is 11.4, but the pupil is only 9.3 at any given time.
Oh, okay.
So you're never using the whole mirror at a time, but the mirror is bigger.
Oh, see, then that's cheating.
And the VLT combines all four telescopes into a single instrument called sphere.
That is true, yes.
So it's a trick question all around.
Yeah. Yeah, and that concludes my talk. So thank you for listening. Oh, okay, and I'm free to take questions. Yes.
So like your adaptive optics, is that primarily a hardware solution or is it like software, hardware integrated?
Yeah, so it's so you asked if the adaptive optics is primarily a software or a hardware solution, and it's basically a combination of both. So actually, I have a clip here which is demonstrating what adaptive optics does, which I wasn't sure I would have time to show, but I think this can explain it better. So what's happening here is that we have light, we have our atmosphere coming in to the telescope, and what we're doing here is we're sensing the atmosphere on a device called a wavefront sensor, and then we're feeding this information to a computer which is doing a bunch of really fast calculations and is then telling this mirror how it should bend in order to correct for our atmosphere. And so this is a pretty kind of a very busy, like, complicated solution, and it involves a lot of moving parts, all of which can be better optimized. But the end result is that you achieve this higher quality image. So it is both hardware and software, because some of the hardware might involve those mirrors that bend, and then the software might involve better optimizing this loop and like how quickly the computer can do its calculations to determine the ideal corrections. So yeah. Yes. So the question was, what was the gas giant? And now I'm forgetting off the top of my head, even though I just had this in the slide before. It's HD 9 something B. Someone might be able to help from the team. No. Okay, well, I'll have to get back to you on that because I can't remember off the top of my head. This is, I believe, from the pup search. Okay. Yes. How many candidates per night? So that really depends, I guess. Or wait, was that your full question? Yeah, so candidates as far as like potential planets. So that depends in part on some bureaucracy because we have to submit telescope proposals for what we want to observe, and they have to be approved. So that largely dictates what we're observing on a given night and how much time we're spending on it, which might not be the most satisfying answer, but... One more question, if there are any. No? Yep.
Yeah.
Thanks.
I don't think I've ever appreciated exactly what AO does until I saw those videos. So that's very impressive. Thank you. And thank you all for joining us tonight. Happy holidays if you celebrate them. Our next show will be, I should have pulled my calendar up, the third Tuesday of January, which is January 21st. So hope you have a wonderful holiday season, Happy New Year, and we will see you in 2025.